fact that he forgot. So yes, it is my fault. They're going to look at it. It's my fault, right? Because I put Walker in charge. All right, let's try problem number 2. Try problem number 2. We're going to roll right through this section as fast as possible. I've got a kid on the playground makes a complete to and fro swing every 2 seconds. The frequency of the swing would be what? Frequency is beats per second, right? So I go through 1 full cycle every how many seconds? So I'm going to go 1 swing every 2 seconds, and so my frequency would be 0.5, what's the units?
Hertz.
Hertz. HGZ, H, capital H, all work. And if I want to find the period, I would simply do what? Period is going to be equal to 1 over the frequency, which is therefore equal to 1 over 0.5, which is equal to 2. Which, by the way, I kind of knew because he goes through a full cycle every 2 seconds, right? So the period of time it takes to go through a cycle is 2 seconds. Have we got this? By the way, we've almost covered all the formulas that are in the formula sheet involving waves already.
So wait, when are we taking this test?
We're taking the test after the AP test.
Oh.
Yeah, we're gonna get through this chapter, get this all straightened out, and then we'll take a deep breath and then blow through the rest of physics because we're still 9-8 line. All right, try number 5.
They've gotten your 7 minutes extra per class.
Oh yeah, that's worked out well for me. Okay, so I have bullets being fired from a gun, right? Number 5. It says a distance in the air between the flying balls. So it says fires 10 rounds every second and has a speed of 300 meters. So after 1 second, how far is the farthest bullet?
300 meters.
Sierra. 300 meters. All right, good job, Sierra. So 300 meters away. And how many bullets have I fired? 10. So how far apart are the bullets?
30.
Sierra?
Hey, I'm more me and Sierra team.
30 meters, right? So each one's going to be 30 meters apart because that's the only that makes sense, right? So to figure this out, I said, well, I've got steady bullets being fired. Okay, that makes perfect sense. I can live with that. So it says, what happens to the distance of the bullets if the rate of fire is increased? If I start speeding up the bullets, rate which is coming out of the gun,
Wait,
what would happen to the distance between the bullets?
the way you said it was
Sierra?
Will they get faster?
But the bullets are going the same speed. The question is, what would happen if I fire more bullets per second? Would the bullets get farther apart or closer together? Closer together, right? Because there'd be more bullets in the same distance, right? And so that's an interesting question. Go ahead and write that down. Make sure you got that down there. And then try number 6, which is what we're getting to, because we're not going to talk about machine guns in this class after this moment. Try number 6. All right. So Walker, some kid is sitting in a puddle, splashing it flashing it 10 times a second. The speed of the waves is 300 centimeters per second. What's the distance between the wavelengths? What's the wavelength of the waves? 30 centimeters. How'd you get that?
Because this is the exact same question. So
Right. So you speed divided by bullets. How far apart how many bullets per second? Bullets per second is what? Frequency. So speed divided by frequency would be equal to the wavelength. Now, some of you are not as familiar with these letters as you should be. This is the letter for wavelength. Now, here is where I've got to take a pause. Who's got a formula sheet for me? I use the letter F, and I use the letter F for years and years and years. I'm wondering if your formula sheet has a V down there, because that's what you said it should have down there. Nobody has a formula sheet. The whole room full that says they're going to do it, supposed to be doing. Oh, they use for F, so we're good. All right. So I won't mention V. By the way, if you're in chemistry, that's the letter V, right? But we don't use that in here apparently. Frequency. Yes? And this is speed. So if you move everything over, velocity equals frequency times wavelength, which is the more normal way in which we write this formula. But you just derived it, right? Because you just, same problem as the bullets one. You knew the bullets one, didn't you? Okay? What this implies, by the way, is if you increase the frequency of a normal wave, the velocity doesn't change, the wavelength changes. Make it faster, you just did it with more waves. Make it slower, less waves. But the speed stays the same. Okay? So, here's the speed formula. Make sure you write that down where it says speed. Now, the one thing about speed that's going to drive you crazy as a physicist is the following sentence. All waves travel at constant speed. Why is that weird? Up until now, we've been talking about things what? Accelerating, right? They're starting at 0. If I make a sound wave, you would think it'd have to accelerate, and then it go ooh, faster, 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 and then finally get to you, right? That doesn't happen. Instead, the moment I make the wave, it propagates at the same speed. Make sense? If that didn't happen, by the way, you would hear some strange conversations. You might hear an answer for the question. Right? Depending on how fast they got to you. Right? That would be a strange world we live in. How does this really work? Well, now we're going to play with Slinky. Let's play with Slinky. Has anybody got the ability to videotape something?
Only all of them.
So 10-6, number 1, or A. Okay, it says that velocity was frequency times wavelength. It says microwaves, electromagnetic travel through space at a speed of 3 times 10 to the 8th meters per second. Frequency is 2450, 1, 2, 3, 4, 5, 6. Oh, I could be wrong. That's enough zeros, it might make a difference. And then wavelength, right? What do you get for wavelength?
Part B. Oh,
Part A.
you need it.
What did it ask for? Oh, it's a period. Oh, I wasn't even doing that right. So I guess you're probably right. Hold on. So just 1 over that, right?
Yeah.
2, 4, 5, 0, 1, 2, 3, 1, 2, 3, boom. You said 4.08?
Yeah.
All right. Times 10 to the negative 10th seconds would be the period. Agreed? And then B, which is the problem I was apparently doing. I better read the question. Yes, I'm doing problem B. 3 exponent 8 divided by 2, 4, 5, 0, 1, 2, 3, 1, 2, 3. Boom. I get 0.122 meters. Which is the theoretical, which is why you're perfectly safe standing in front of a microwave, in spite of the fact you've heard all the stories about people who microwaved and radiation and whatever else. In the front of your microwave, you have a mesh, right? That mesh is metal. Light, when it strikes a metal thing, runs electrons in the wire and disappears. As long as your mesh is smaller than that wavelength, nothing from the microwave can get out. Now, if you destroy the safety latch and open it up and turn on your microwave so it's running when the door's open, that mesh is no longer in your path, and yes, you can microwave yourself.
What would it do?
It'd cook you.
Really?
Yeah.
Like it's so cool.
Yeah.
How do microwaves do different things? I've heard different things like they shake.
The answer to the question is, this is exactly, when properly made, exactly a couple thousand times the length of a water molecule. Because of that, it shakes water molecules in what's called resonance. And we'll talk about resonance in a little bit. But what it means is that all the water molecules shake like crazy when everything else is kind of like, what's going on? So all the energy, all the heat energy goes right through water molecules, which shakes the heck out of them, which cooks the food around them, because as you know as an AP chemistry student, all temperature is the shaking of molecules. That's all it is. It's how fast your molecules are moving. Don't give me, hold on.